Welcome to the deep dive. Today we're plunging into something fundamental yet, well, surprisingly powerful. Pressure. You might think it's just about a huge force, maybe, but the real story, it seems, is how that force gets spread out.
Exactly. Like, picture that rectangular block you mentioned. If you stand on its skinniest edge,
Right.
all its weight hits this tiny spot. Huge pressure.
But then lay it flat.
Same weight, totally different story. Much less pressure on the table because the area is, bigger. It's all about that distribution.
That block example really clicks. It shows straight away it's not just the push, but where it's pushing.
Yeah. And formally, we define pressure as the force acting sort of squarely or normally on a unit area.
Okay, so force F, area A, pressure P is just F divided by A. Simple enough.
Pretty much. And sometimes, especially with fluids, we talk about thrust, it's basically the force acting straight down, perpendicular to a surface.
Like water pushing down on the bottom of a tank.
Exactly that. So you could also say pressure is thrust divided by area in those cases.
Got it. So it's measured in newtons of force per square meter of area, which gets its own name, right? The Pascal. PA for short.
That's the one, the SI unit.
Okay. So our mission for this deep dive, looking at our sources, is to really unpack this idea of pressure. We'll look at solids, then liquids, and even the air around us, atmospheric pressure.
And hopefully find some of those, surprising applications and key takeaways.
Yeah, things that might just make you look at everyday stuff a bit differently. Let's start by pressing down on solids then.
Sounds good. And that core relationship we touched on between pressure, force, and area, that's key.
Right. Pressure and force go hand in hand.
Directly linked. Double the force on the same spot, you get double the pressure. Easy.
But area is the opposite.
Inverse relationship, yeah. Spread that same force over twice the area and the pressure gets cut in half.
And you see this everywhere, don't you? Like a simple nail.
Oh, absolutely.
The pointy end has this teeny tiny area.
Almost nothing.
So even a decent tap with a hammer creates huge pressure right at that tip, enough to go into wood.
But try hitting the flat head of the nail with the same force.
Nothing happens. Well, practically nothing. Same force, different outcome because of the area.
It's the exact same idea behind a sharp knife or an axe blade.
Ah, okay.
That cutting edge is ground incredibly thin to minimize the contact area.
So even a small push along the blade translates into enough pressure to slice through things.
Yeah. Think about animal claws, too. Or teeth. Sharpness concentrates the force.
And then the opposite situation. Those huge trucks, the lorries you see on the road.
Right, they don't just have 4 tires.
No way, they have loads. 8, 10, even more sometimes.
And that's all about spreading their massive weight over a much larger contact area with the road.
Reduces the pressure at any one point.
Exactly. Stops them from damaging the road surface too much. It's clever engineering based on a simple principle.
Or think about camels in the desert.
Their feet, they're so wide and flat.
Like natural snowshoes, almost. Spreads their weight so they don't just sink into the sand.
Same reason skiers use long, wide skis on snow, distributes the weight.
You float on top instead of plunging in. And buildings, too. Skyscrapers.
Definitely. Ever notice the foundations? They're massive, incredibly wide.
To spread out the colossal weight of the building.
Precisely. Prevents the whole thing from sinking into the ground. It's pressure management on a huge scale.
It's pretty amazing how this basic physics concept pops up in so many different ways. Okay, let's crunch some numbers quickly. Our materials have a couple of examples. First one, an 80 Newton solid. Contact area is 1.6 square meters.
What's the pressure?
Okay, so basic formula. Pressure, force, area. That's 80 newtons divided by 1.6 square meters.
Right.
Which comes out to 50. 50 newtons per square meter or 50 pascals.
50 pas. Okay. Straightforward. Example 2. A rectangular wooden block weighs 25 newtons. Its contact area is 25 centimeters by 10 centimeters. What's the pressure there?
All right, first thing, I got to watch the units. We need the area in square meters. Right. Centimeters won't work.
Nope. So 25 centimeters is 95 meters. 10 centimeters is 0.1 meters. Multiply those.
Gives you 0.025 square meters.
Spot on. 0.025 square meters. Now, we take the force, 25 newtons, and divide by that area.
25 divided by 0.025.
Comes out to 1,000. 1,000 newtons per square meter or 1,000 pascals.
Wow. Okay. So even though it's lighter than the first object, the much smaller contact area means the pressure is way higher.
Exactly. Really shows that inverse relationship with area in action. Okay, ready to move into liquids?
Absolutely. Liquids are different, aren't they? They don't hold their own shape.
Nope, they conform to their container, but they definitely exert pressure.
Not just downwards. Because of their weight.
Downwards, yes, but also sideways, against the walls of the container.
Why sideways too?
It's the molecules. They're always moving, bumping into each other, bumping into the walls. That constant bombardment creates the pressure, that outward thrust.
Okay. And there's a simple experiment to show this, right? With a tube and a rubber sheet.
Yeah, it's a good one. Take a glass tube, maybe open at both ends, and stretch a thin rubber sheet over one end, like a drum skin.
Okay.
Hold it upright, rubber end down, and start pouring water in. You'll see that rubber sheet bulge outwards.
Ah, because of the water's weight pushing down.
Exactly. And here's the key bit. The more water you add, the deeper the water column gets, the more it bulges.
So pressure increases with depth. Makes sense.
Directly shows that connection.
And how do we actually measure this pressure in liquids? There's a device, a manometer.
That's it, a manometer. Usually it's a U-shaped glass tube, partly filled with a liquid, often mercury or maybe colored water, something easy to see.
Okay, a U-tube.
One side of the U is typically open to the air, giving you a baseline atmospheric pressure. The other side connects to whatever you're measuring.
How does it connect?
Often through a flexible tube ending in something like a small funnel covered with a membrane, which you dip into the liquid you're testing.
I see. So you dip the funnel end in.
Right, and the pressure of the liquid you're testing pushes on that membrane. That push is transmitted through the connecting tube to the liquid in the U-tube.
Causing the levels in the U-tube to change.
Exactly. The difference in the height of the liquid in the two arms of the U tells you the pressure difference compared to the atmosphere, or the gauge pressure of the liquid at that point.
Clever. And using manometers like this, we've figured out some key things about liquid pressure.
Absolutely. Several fundamental characteristics. First, as we saw with the bulging rubber sheet, pressure definitely increases with depth.
Deeper you go, higher the reading on the manometer.
Precisely. Second, and this is really interesting, at any specific depth within a liquid, the pressure is the same in all directions.
Wait, all directions. Sideways, upwards, downwards.
All of them. You can take that manometer's funnels, keep it at the same depth, but turn it facing up, facing down, facing sideways. The reading stays the same.
That's kind of counterintuitive.
Isn't it? But it's true. And it has real-world consequences. Think about dams.
They're always thicker at the bottom than the top.
Why? Because the water pressure pushing outwards against the dam wall gets much, much greater the deeper you go. The base needs to be strong enough to withstand that immense sideways force.
Okay, that makes sense now. Pressure increases with depth and acts in all directions. What else affects liquid pressure?
Density. The density of the liquid itself matters.
Heavier liquids exert more pressure.
For the same depth, yes. Imagine you have two identical containers filled to the same level, one with water, one with, say, oil, which is less dense.
Okay.
The pressure at the bottom of the water container will be greater than the pressure at the bottom of the oil container. More mass packed into the same volume means more weight pushing down.
Got it. Density plays a role. And you mentioned sideways pressure before.
Yep. Liquids definitely push sideways. You can show that too. Take a can or tube, make a hole in the side, and attach a balloon over the hole.
Okay.
Fill the container with water. As the water level rises above the hole, the balloon starts to inflate outwards.
Demonstrating that sideways push.
Exactly. And one more cool property. Liquids always find their own level.
What does that mean?
If you have several containers of different shapes and sizes, but they're all connected at the bottom.
Like with tubes.
Yeah. And you pour water into just one of them, what happens?
The water spreads out.
It does, and the surface of the water will end up at the exact same height in all the connected containers. Regardless of their shape, it seeks its own level.
Like they're all balancing out. Fascinating. Okay, so liquids exert pressure. It increases with depth, acts everywhere, depends on density.
Yeah.
Now, how does this pressure get transmitted through a liquid? That leads to Pascal's law, doesn't it?
It does indeed. Pascal's law. Named after Blaise Pascal, brilliant scientist and philosopher.
What does it state?
It's actually quite elegant. It says that if you have a liquid that's enclosed, confined.
Like in a sealed container.
Right. And you apply pressure at any point on that liquid, that pressure is transmitted equally and without diminishing in all directions throughout the entire liquid.
Equally and undiminished. Everywhere.
Everywhere. It spreads out instantly and uniformly.
Is there a classic way to show this?
There is. Our sources describe using a flask, maybe round, filled completely with water. It has a piston at the neck so you can push in, and lots of little holes drilled all over its surface.
Okay, a leaky flask with a plunger.
Sort of, yeah. When you push down hard on the piston, what do you think happens?
Water squirts out of the holes.
It does. But the key observation is that it squirts out of all the holes with pretty much the same force, the same velocity.
Showing the pressure you applied with the piston got spread evenly to every part of the flask, pushing water out everywhere equally.
Exactly. That's Pascal's law in action.
And this isn't just a neat party trick. It has some really big consequences.
Huge consequences. Think about the deep ocean. The pressure down there is enormous.
Because of the immense weight of all the water above.
Right. It gets so high it can crush submarines that aren't built strong enough, and humans absolutely need special protective suits for deep dives.
And deep-sea fish. You bring them up too quickly.
They often burst, unfortunately. Their bodies are adapted to withstand the high external pressure of the deep. When that external pressure is suddenly removed at the surface, their internal body pressure isn't balanced anymore, and, well, it's not good.
A grim illustration of pressure balance.
Yeah.
But Pascal's law also leads to something incredibly useful: hydraulic systems.
Yes, this is where it gets really powerful technologically, the hydraulic machine.
Explain how that works. It involves different size pistons.
It does. Imagine you have two cylinders connected by a pipe, both filled with a liquid, maybe oil. Each cylinder has a piston that can move up and down. Crucially, one cylinder and its piston are much smaller than the other.
Okay, a small piston and a big piston connected with liquid inside.
Right. Now, if you push down on the small piston with a certain force, you create pressure in the liquid. Let's say force F1 on area A1 creates pressure P.
Okay, P equals F1 A1.
Now, Pascal's law says that this pressure P is transmitted undiminished through the liquid to the large piston.
So the large piston feels the same pressure P.
Exactly. But the large piston has a much bigger area. Let's call it A2. The force exerted by the liquid on this large piston, F2, will be pressure P times area A2.
And since A2 is much bigger than A1...
F2 will be much bigger than the initial force F1 you applied. You've multiplied the force.
Wow. Small push in, big push out.
That's the magic of hydraulics. It's used in car brakes, hydraulic lifts, construction equipment, countless applications where you need to generate large forces.
Amazing. Now, the sources also bring up something relatable. Feeling lighter in a swimming pool.
Oh, yes, that sensation.
Is that just buoyancy, or is pressure involved too?
It's closely related. Buoyancy itself is an upward force exerted by the fluid. But where does that force come from? It comes from the pressure of the water. Remember, pressure increases with depth.
Right.
So the water pressure pushing up on the bottom surface of your submerged body is slightly greater than the water pressure pushing down on the top surface.
Because the bottom surface is deeper.
Exactly. That difference in pressure results in a net upward force, the buoyant force. So yes, the water pressure pushing up on you definitely contributes to that feeling of being lighter. It counteracts some of your weight.
Okay, that clarifies the connection. Right, so we've covered solids and liquids. Shall we look upwards now? To the air. Atmospheric pressure.
Let's do it. The atmosphere, this huge blanket of air surrounding our planet.
It goes up pretty high, doesn't it? Almost 300 kilometers, according to the sources.
Yeah, though it gets incredibly thin way up there. Most of it is concentrated much lower down. The density decreases rapidly with altitude.
And just like water has weight, this massive column of air pressing down on everything has weight too.
Absolutely. And the pressure caused by the weight of that air column acting on a unit area of surface is what we call atmospheric pressure.
And it's surprisingly large.
It really is. At sea level, on average, it's about 100,000 pascals. That's 1.01 times 10 to the power of 5 pascals.
The sources had that wild analogy, like having 2 elephants standing on your head.
Yeah, it sounds completely crushing. So the big question is, why don't we get crushed?
Our bodies must be pushing back somehow.
Exactly. We have pressure inside us, our blood pressure, the air pressure within our lungs and body cavities. This internal pressure pushes outwards and balances the external atmospheric pressure pushing inwards.
So we're in equilibrium.
Pretty much, yeah. We're adapted to live under this constant pressure.
How can we actually prove that air exerts this pressure? There are some neat experiments, like the postcard and glass of water.
Oh yeah, the inverted glass trick. Classic. Fill a glass right to the brim with water.
No air bubbles.
Right. Slide a flat, stiff piece of card, like a postcard, over the top. Hold it flat, and carefully turn the whole thing upside down over a sink, just in case.
Okay. Holding my breath.
Now, gently take your hand away from the card.
These cards stays put. The water doesn't fall out.
Magic. Nope. It's the atmospheric pressure pushing up on the outside of the card. That upward force is greater than the downward force from the weight of the water inside the glass.
So air pushes up too, not just down.
Absolutely. Which leads to the other really dramatic one, the crushing can experiment.
I think I've seen this one. You need an empty metal can, like a drinks can.
Yep. Put a little bit of water in the bottom, just a splash.
Then heat it up.
Heat it strongly. On a stove or burner, you want the water inside to boil vigorously, filling the can with steam.
So the steam pushes the air out.
Exactly. Once it's steaming well, you carefully, using tongs probably, take the can off the heat and immediately seal the opening. Maybe screw a cap on if it has one, or quickly invert it into a trough of cold water so the water seals the opening.
Okay, it's sealed, full of hot steam. Then what?
Then you cool it down rapidly. Pour cold water over it or plunge it into the cold water bath.
The crunch, the can just collapses inwards, right? Violently.
It does. It implodes. Why? Because when that hot steam inside cools down, it condenses back into a tiny amount of liquid water.
Creating a vacuum. Or near enough.
A very low pressure inside, yeah. A partial vacuum. But the atmospheric pressure outside is still pushing hard on the can from all directions, top, bottom, sides.
And now there's hardly any pressure inside pushing back out.
So the huge external pressure just crushes the can. It's a really powerful demonstration that air pressure is real, significant, and acts in all directions.
And coming back to the two elephants thing.
Yeah.
That do you know fact. It reminds us we live under this immense pressure, but the air inside us, thanks to breathing, balances it out.
Fascinating. And we see effects of this atmospheric pressure in everyday things, too.
All the time. Rubber suction pads are a great example.
How do they work again?
You press the cup against a smooth surface, right, that forces most of the air out from underneath it.
Creates a seal.
Yeah. Then the higher atmospheric pressure outside the cup pushes it firmly against the surface because there's very little air pressure underneath pushing back.
So it's the atmosphere holding it on, not really suction.
Precisely. Same idea with drinking straws.
Oh, yeah.
When you suck on a straw, you're reducing the air pressure inside the straw.
Lowering it. And the higher atmospheric pressure pushing down on the surface of the drink in your glass then forces the liquid up the straw into your mouth.
The atmosphere pushes the drink up. I never thought of it that way.
It does. And old fountain pens, filling them.
You squeeze a bladder or work a piston.
Which creates a low pressure area inside the pen. Atmospheric pressure on the ink in the bottle then pushes the ink up into the pen's reservoir.
Okay. What about lizards on walls? That seems like suction.
Their feet are amazing. They have specialized structures, tiny hairs or pads that create a very close contact, possibly forming many tiny low-pressure zones. Atmospheric pressure then helps hold them there.
Incredible. And syringes.
Same principle as the straw, basically.
Right.
Pulling back the plunger lowers the pressure inside the syringe barrel.
Allowing the higher atmospheric pressure outside to push the liquid in.
Yep. And think about high altitudes again.
Lower atmospheric pressure up there.
Right. Which can sometimes cause nosebleeds in people not acclimatized. The internal blood pressure is relatively higher than the reduced external air pressure, and fragile capillaries can rupture.
Makes sense. So astronauts and high-altitude mountaineers need special gear for this reason.
Absolutely essential. Astronauts in space face near zero external pressure. Their suits have to provide the necessary pressure to keep them alive. Mountaineers at extreme altitudes also need oxygen and sometimes pressurized environments because the air is so thin and the pressure so low.
Wow. Okay, so atmospheric pressure is a big deal. How do we actually measure it accurately? It changes, right?
It does. It changes with altitude, as we've said, highest at sea level, decreasing as you go up. It also changes with weather conditions. High pressure usually means stable weather. Low pressure can mean storms are coming.
And the instrument is a barometer.
Correct. The barometer measures atmospheric pressure.
The original one was Torricelli's, with mercury.
Yes, Evangelista Torricelli back in the 1640s. His setup was ingenious and surprisingly simple.
How did he do it?
He took a long glass tube, about a meter long, sealed at one end. He filled it completely with mercury.
Why mercury? We'll get to that maybe, but filled it right up.
Filled it right up, carefully getting rid of any air bubbles. Then he put his finger over the open end, turned the tube upside down, and submerged the open end into a dish or trough also containing mercury.
Okay, tube inverted, open end under the mercury level in the dish.
Then he took his finger away. What happened was some of the mercury flowed out of the tube into the dish, but not all of it. The mercury column inside the tube dropped, leaving a space at the top.
A space. What was in the space?
Nothing, or almost nothing. A vacuum. We call it the Torricellian vacuum.
Okay, so a column of mercury left standing in the tube with vacuum above it. How high was the column?
At sea level, under standard conditions, the mercury column stood about 76 centimeters, or 760 millimeters high, measured vertically from the surface of the mercury in the dish.
And why did it stop there? Why didn't it all run out?
Because the weight of that 76-centimeter mercury column exactly balanced the pressure exerted by the atmosphere pushing down on the surface of the mercury in the open dish.
The atmosphere holding it up. So the height of the mercury column is a direct measure of atmospheric pressure.
Precisely. Higher atmospheric pressure can support a taller column. Lower pressure results in a shorter column. And Torricelli found that the width of the tube didn't matter, nor did tilting the tube. As long as you measure the vertical height, it stays the same for a given pressure.
Clever. And we can calculate the pressure from this height. There's a formula.
Yes, the pressure exerted by any fluid column is P equals HdG.
Height times density times gravity.
Right. H is the vertical height of the column, 0.76 meter for standard sea level pressure.
Yeah.
D is the density of the liquid. For mercury, it's about 13,600 kilobinars. And G is the acceleration due to gravity, about 9.8 meter peters.
So multiply 0.76 by 13,600 by 9.8.
And you get a number very close to 104,300 pascals, which is the standard atmospheric pressure we mentioned earlier.
It all ties together. Now, why mercury? Why not water?
Good question. Several reasons mercury is ideal. One, it's incredibly dense.
So you only need a relatively short column.
Exactly. To balance atmospheric pressure with water, which is much less dense, you'd need a column over 10 meters high. Not very practical for a lab instrument.
Okay, yeah, 76 centimeters is much better than 10 meters.
Also, mercury doesn't stick to glass very much, so it gives a cleaner reading, and it's opaque and shiny, making the level easy to see.
Are there downsides to the simple mercury barometer?
There are. It's fragile glass tube open dish of mercury. Mercury itself is toxic, so spills are hazardous. It needs to be kept perfectly upright for an accurate reading, and the open surface in the dish can collect impurities.
So not ideal for carrying around or for everyday use, maybe. Is there an alternative?
Yes, the aneroid barometer.
Yep.
Much more convenient. Aneroid means without liquid.
Okay, no mercury involved. How does it work?
It uses a small, partially evacuated, sealed metal box or capsule. The top of this box is thin and flexible, kind of like a diaphragm. Changes in the external atmospheric pressure cause this thin top to flex. It gets pushed in slightly when pressure rises and springs out slightly when pressure falls.
Tiny movements, presumably.
Very tiny. But these small movements are cleverly amplified by a system of levers and springs.
Which then move a pointer.
Exactly. A pointer moves across a dial that's been calibrated often by comparing it to a mercury barometer to show the atmospheric pressure directly.
Much more robust and portable.
Definitely. And this aneroid mechanism can be adapted for another purpose too, measuring altitude.
An altimeter. How does that work?
Well, we know atmospheric pressure decreases predictably as you go higher.
Right. Lower pressure means higher altitude.
So you can just change the scale on the aneroid barometer's dial. Instead of marking it in pascals or inches of mercury, you mark it in feet or meters of altitude.
Based on that known relationship between pressure drop and height gain, what was the rough figure?
Our sources mention about a 1 centimeter of mercury drop in pressure for every 125 meters you ascend, approximately, especially at lower altitudes.
So the altimeter in a plane or a hiker's watch is basically just a repurposed aneroid barometer.
Fundamentally, yes. Pretty ingenious.
It really is. So that brings us through solids, liquids, gases, pressure everywhere. We've gone from nails and knives, through dams and hydraulics, to the air we breathe, weather forecasting, and even measuring how high up we are.
It's quite a journey, all stemming from that basic idea of force spread over an area. P equals F over A.
Amazing how fundamental it is. It really makes you think. We've talked about dams and submarines resisting pressure and hydraulics using it.
What other ways has nature, or maybe engineers, found to actually harness or work with this atmospheric pressure that's always there, beyond straws and suction cups?
That's a great question to ponder. There must be countless subtle examples, maybe even biological ones, where that constant pressure is either a challenge to overcome or perhaps an energy source or stabilizing factor that's cleverly utilized. Something to keep an eye out for. Definitely something to think about. Exploring how this core concept plays out in places we haven't even considered today. Well, that wraps up our deep dives into pressure. Thanks for exploring it with us.